I'm not using that like 2% of them. Yes. I'm not using 2% of that on that. It looks like you can say, but I don't know. I have any outfits. But mine's like related to like this. So I'm not actually. So mine's one of those, and like none of that. I feel like we think so much about any of it. It's like this is all. It's like I would like one dimension, but I would like each of them was like, okay, I'm done. This is going to be the same. Yeah, but I did. They both like, yeah. It's the same. I'm so sure. She graded it and then like totally looked it. Like it wasn't too bad.
Are you available today?
And I'll be going in my office. I'm available in my office until 3:30 today, except during the X period. Okay, folks. First of all, I just wanted to make an announcement. I will be updating Blackboard this morning. And so look for a ton of uploads. I will also put in active homework. So my goal is to leave here, go back to my office and get that accomplished. Um, as many know, I did grade your exam over the weekend and I posted the grades. What I'm gonna do is I'm gonna have you stop by my office to pick up your exam, or you can wait until Thursday to pick it up. I have one person that still needs to take the exam. So, I won't be handing it back in class today, but you can come get it if you would like, as soon as class is over, or you can wait until Thursday to get it. Now what we're gonna do is we're gonna get into today's information. We're going to start, so what we are doing is we started the process of working with stoichiometry. Basically, stoichiometry is a fancy technical word for chemical mathematics, involving dimensional analysis. Now, dimensional analysis by definition is converting from one dimension to another. Or in other words, converting between units. Now, this is a little bit different than dimensional analysis because not only are we potentially converting between units, but we're converting between substances as well. Now, we have already developed 4 conversion factors that we will be using in the process of these calculations. One of those is the molar mass. The molar mass is a unit that is a conversion factor that allows us to convert between grams of a substance and moles of that same substance. Another one that was developed is Avogadro's number. Avogadro's number is a way to convert between atoms of an element, molecules of a compound, or ions of an element, or ions of a polyatomic ion, and moles. So in these first 2, when we're talking about conversions, the key things that I note when I'm looking at conversions is on this first one, if I see grams, my mind automatically goes to the molar mass. When I see atoms, molecules, or ions, my mind is automatically going to go to Avogadro's number. And then the third conversion factor that we have developed is the mole to mole ratio. And it's used to convert between substances with different formulas. So the key here is substances with different formulas. That is my go-to to tell me that I'm going to need a mole to mole ratio. Now, we've actually got 2 sources for the mole to mole ratio. The very first source is the actual chemical formula and the subscripts within that formula. Because the subscripts within the formula provide a mole to mole ratio between the compound and an element within that compound. And then the second mole to mole ratio we've developed is the balanced chemical equation, specifically the coefficients of the balanced chemical equation. The coefficients of the balanced equation provides a mole to mole ratio to convert between 2 substances within the reaction. So what we're going to be doing today is we are going to be applying our stoichiometry to chemical reactions. And certain terms are going to result from this process. One term that is going to result is going to be the limiting reactant. This will be the reactant that is used up in its entirety during the reaction. Another term that we're going to encounter is going to be that of theoretical yield. This is the amount of product that can be formed in theory. We will also talk about the actual yield. And this is the yield of product obtained during a reaction. Just so you know, the theoretical yield is always determined from calculation. Whereas the actual yield is always going to be given to you. And the last term we will encounter as part of this product is going to be the percent yield, or the part of this process. And it is the actual yield divided by the theoretical yield times 100. Okay, so I've gone over all the definitions. I've gone over all the conversion factors associated with what we're about to do. Let's just jump into some problems and work through them. I think that is the best way to start to understand all of these definitions and conversion factors is by applying them. When copper 2 chloride reacts with sodium nitrate, copper 2 nitrate, and sodium chloride, are formed. A, we're going to write and balance the reaction. B, if 15 grams of copper 2 chloride react with 20 grams of sodium nitrate how much sodium chloride can be formed? C, identify the limiting reactant. D, how many grams of copper 2 nitrate can be formed? E, what mass of excess reagent remains? And F, if 11.3 grams of sodium chloride are actually formed, in the reaction, what is the percent yield? I will say this question pretty much asks every possibility there is associated with a chemical reaction. Okay, the first thing we've got to do is figure out our reaction. Whoa, where did it go? First of all, we have copper 2 plus combining with chloride. So the formula is CuCl2 reacting with sodium nitrate, Na plus, NO3 minus. So the formula is NaNO3. Going to form copper 2 nitrate, Cu2 plus, and NO3 minus. So that's going to be CuNO3 2. And sodium chloride, Na plus Cl minus. So that's NaCl. So those are our reactants and our products. We then need to balance this reaction. And to balance this reaction, you're going to need 2 sodium nitrates and 2 sodium chlorides. Questions about the first one? I think I need to let people catch up with me. B. Okay, before I get into actually answering B, I want to point out something. I have 15 grams of copper 2 chloride and I have 20 grams of sodium nitrate. So the thing I wanted you to note is you have masses given for both reactants. And so this is a limiting reactant problem. Now, when I see that, the reason that that is important is it tells me how I'm going to approach the problem. First, I'm going to convert each reactant into the desired product. Then I'm going to evaluate the results. Because the result that is the lowest is the theoretical yield. And the result that is the lowest came from the limiting reactant. So I was given up here in part B, so what I'm going to be doing is I've got 15 grams of copper 2 chloride. And I want to know sodium chloride. I also was given 20 grams of sodium nitrate, and I want to know sodium chloride. Okay, now this is going to go back to our conversion factors we've developed. First thing I note, different substances. which means I'm gonna need the mole to mole ratio. According to the balanced chemical equation, for every 1 mole of copper 2 chloride, there is 2 moles of sodium chloride. Next thing I note is I am dealing with grams of copper 2 chloride. Grams means molar mass. Copper has a mass of 63.55. Chloride has a mass of 35.45 each. So the molar mass for copper 2 chloride is it's 134.45 grams. Is equal to 1 mole. The next thing I notice is that I have grams of sodium chloride. Grams means molar mass. Sodium has a mass of 22.99. And chlorine a mass of 35.45. So this has a mass of 58.44 grams of sodium chloride is equal to 1 mole of sodium chloride. Once you've identified your possible conversion factors, you're ready to start the math with the thing you are given, which is the 15 grams of copper 2 chloride. Your first conversion factor will need grams of copper 2 chloride. So I'm going to use the number 2 here. Now I've got grams of copper 2 chloride in the numerator, so I need grams of copper 2 chloride in the denominator. With the mole portion going into the numerator. The gram portion went into the denominator so that the substance and the unit canceled. Now I'm ready to do the, now I have moles of copper 2 chloride, so I need a conversion factor with moles of copper 2 chloride. That is going to be the second one. I'm going to place the mole of copper 2 chloride in the denominator and the moles of sodium chloride in the numerator. The moles of copper 2 chloride had to go in the denominator so that the unit and the substance would cancel, leaving moles of sodium chloride. But I want to convert it into grams of sodium chloride, so I'm going to use its molar mass. I'm going to place the mole of sodium chloride in the denominator with the mass of sodium chloride in the numerator. Again, the moles of sodium chloride had to go in the denominator so that the unit and the substance would cancel, leaving grams of sodium chloride. So that is 15 divided by 134.45 times 2 times 58.44. That is a value of 13.0 4 grams of sodium chloride. We're going to do the same thing with our next one. Again, I'm going to start by breaking it apart. Sodium nitrate, sodium chloride, different substances. So I need, if I've got different substances, that means I'm going to need the mole to mole ratio. According to the balanced chemical equation, there were 2 moles of sodium nitrate per 2 moles of sodium chloride. The next thing I notice is I have grams of sodium nitrate. So I'm going to, grams tells me I'm going to need the molar mass. Sodium has a mass of 22.99, nitrogen a mass of 14.01, and oxygen a mass of 16. So that is 85. The next thing I notice is that I need grams of sodium chloride. Again, grams tells me I'm going to need the molar mass. Which we calculated previously as 58.44 grams of sodium chloride is equal to 1 mole of sodium chloride. Now that I've come up with the possible conversion factors, I can begin this calculation with what I was given, which is the 20 grams of sodium nitrate. My first conversion factor is going to need to have grams of sodium nitrate, and therefore I'm going to be using the molar mass of sodium nitrate. The gram portion of that equality is going to go into the denominator so that the mole portion goes into the numerator. The gram portion had to go in the denominator so that the unit and the substance would cancel out. And you're left with moles of sodium nitrate. The next thing needs moles of sodium nitrate, so we're going to be using our mole to mole ratio. 2 moles of sodium nitrate is to 2 moles of sodium chloride. The sodium nitrate was placed in the denominator so that the unit and the substance would cancel, leaving moles of sodium chloride. Now I can use my molar mass of sodium chloride. The mole portion will go in the denominator with the mass portion in the numerator. The mole portion had to go in the denominator so that the unit and the substance canceled. And once I've got that, I am ready to perform this calculation. And you get an answer of 13.75 grams of sodium chloride. So going back to the question for B, the question was, how much sodium chloride can be formed? The answer is 13.04 grams of sodium chloride can be formed because, and this will be the theoretical yield too. Questions? Yes.
In the container for stuff, I'm not really sure which one. But I think it's supposed to be 85 grams, but it ain't.
You're right. But it doesn't change, but that, it changes that, but not the process. But yes, that was supposed to be grams. Yes.
Okay, so you take like the smaller one always when you find it, right?
What do you mean the smaller
So
one?
like 13.04 is like less. than 13.05.
That's correct. To figure out which one's the theoretical yield. Whichever one's the smaller is going to be the theoretical yield, which is the maximum amount that could be formed. And even though it's a little bit later on, what we can say now is that our CuCl2 is the limiting reactant. Which that's the answer to, oh, C. So this is the answer to C right here. Other questions? Now, folks, you don't have to write out everything I'm writing out on that right-hand side. I'm trying to help you learn the mental process. You can just do the math, but I'm trying to help you learn the mental process. So I'm giving you, because of this, this is how I think. Because of this, this is how I think. And that's what I'm showing you on that right-hand side over there. Once you do enough of these, you can skip that right-hand side. Now, I want to show you something. If you have your flow chart, didn't I pass these out last week? I've lost track of time and what I've done and not done. It looks, not that you can see it well, but it looks like this. So it's got a top row, some wording, a middle row, some wording, and a bottom row. And I do have extras if you don't find yours. Oh, if you don't like my method of this is how I think, and so this is what I do, which is what this right hand side was, you can also use the flow chart. I wanted to go from grams of one substance to grams of another substance. Grams of one substance on the far left-hand side, grams of another substance on the far right-hand side. On the arrows, it tells you what the conversion factor has to be. So if I start from the left-hand side, my first conversion factor is the molar mass. My second conversion factor is the mole to mole ratio. My third conversion factor is the molar mass. So you can actually follow the flow chart also. To help you figure out what conversion factor to do when. Based off of what you're needing to accomplish. So that's another tool. I prefer to be able to think through that because I'm not always going to have the flow chart. Whereas if I know the thought process, it helps. Okay, so D. Asked how many grams of copper 2 nitrate can be formed. Well, folks, you're going to start with the limiting reactant here. So we're going to have to start with our 15 grams of copper 2 chloride and go to grams of copper 2 nitrate. Does anyone want to tell me why I had to start with copper chloride? Copper 2 chloride. Because it's a limiting reactant. When copper 2 chloride, basically what a limiting reactant is telling you is when it runs out, you're done. You can't go any further. So we have to do this one. Now, the process is going to be the same. Because of that, I'm not going to write it all out. Going to start with 15 grams of the copper 2 chloride. Which had a molar mass of 134.45. I'm then going to use my mole to mole ratio. For every 1 mole of copper 2 chloride that we use, we get out 1 mole of copper 2 nitrate. And then I'm going to need the molar mass of copper 2 nitrate. So if I get to the beginning. Which is 87.57 grams of copper 2 nitrate is 1 mole of copper 2 nitrate. So the maximum I can form of the other conversion of the other material is going to be equal to 20.93 grams of copper 2 nitrate. Questions? E asked me how much of what mass of excess reactant remains. Again, folks, the limiting reactant tells you everything. It tells you when the reaction is going to stop. Because when it runs out, everything is out. It cannot go further. So what you're going to do in the case of E is you're going to convert the limiting reactant into the second reactant or the excess reactant. Then you will subtract the value obtained from the original quantity. So we're going to take that 15 grams of CuCl2 and we're going to be converting it into sodium nitrate. So 15 grams of CuCl2. We have 1 mole of CuCl2 is 134.45 grams. Now we do the sodium nitrate. Oh. Which was 85, or no, I'm sorry, we do the mole to mole ratio. For every 1 mole of copper 2 chloride, we need 2 moles of sodium nitrate. And then we're going to use the fact that 85 grams of sodium nitrate is equal to 1 mole of sodium nitrate. So 15 divided by 134.45 times 2 times 85 means, if I could type correctly, means that we need 18.97 grams of sodium nitrate. So the amount in excess is going to equal 20 grams minus the 18.97 grams, or in other words, 1.03 grams of sodium nitrate was in excess. Finally, we're asked for the percent yield. Percent yield is the actual yield divided by the theoretical yield times 100. So that's going to be equal to the actual yield, which was given to us in the original problem, of 11.3, divided by the theoretical yield, which was 13.04, times 100. And you get an 86.7 percent yield. Questions? Yes,
Was the 20 grams of you from the 20 grams of?
that was given in question part A. Okay. Any questions about stoichiometry? We've done several types of stoichiometry problems. With balanced reactions, calculated molar mass. Any questions about stoichiometry thus far? It was in the original problem. It will, if you look back when I was talking about percent yield and actual yield and theoretical yield, the theoretical yield came from the calculation you performed. The actual yield always has to be given to you in the problem. Okay. So now what we're going to do is we're going to get into probably what I hate to say this, but the most difficult of the stoichiometry. And what we're going to get into is we're going to get into molarity. With molarity, we are going to learn to calculate molarity. Given the mass of substance and the volume. We are going to use molarity as a conversion factor in two ways. The first way that we're going to use it as a conversion factor is simply to convert between moles and volume of the same substance. The second way that we're going to use molarity is as a conversion factor in stoichiometry. In other words, we're going to either replace the molar mass, well, we're going to replace the molar mass with molarity. And the third thing we're going to do is we're going to Use molarity in dilution calculations. But we're gonna start off simple and straightforward with number one here. But before we do that, we need to talk some more terms. First of all, there is the solute. The solute is the substance that changes state of matter or if both substances are the same state, it is the minor component. The solvent is the substance that dissolves the solute. The two together make up the solution. Molarity is represented with a capital M. And by definition, it is equal to the moles of solute divided by the liters of solution. So now let's look at an example. What is the molarity of a solution that was prepared by dissolving 14.2 grams of sodium nitrate with its molar mass equal to 85.0 grams per mole in enough water to make 350 milliliters of solution. Okay, I am looking at this definition right here. And the first thing I note is I need the moles of solute. So I'm going to take that 14.2 grams of NaNO3 and convert it into moles of NaNO3. To do so, I'm going to use the molar mass of NaNO3. So it's zero, huh? Oh, I'm at 14.2. So it's 0.167 moles of NaNO3. Step B. Is I need liters of solution. So I'm going to take that 350 milliliters and convert it into liters. There's 1,000 milliliters in a liter. So that means I have 0.350 liters of solution. Now that I have the two components for the formula molarity, it is a matter of applying the formula. So the molarity is going to equal moles of solute over liters of solution. Which is going to be 0.167 moles over 0.350 liters of solution. So you get a molarity of 0.477 molar NaNO3 as your answer. Questions? And I know you've seen concentration units in biology if you're in biology right now. But it doesn't hurt to repeat this because considering molarity still gives students fits, even if they've seen it in biology. Okay, so let's look at one more example. Yes, I know. Trying to get through class. What is the molarity of a solution that was prepared by dissolving 82 grams of calcium chloride in enough water to make 812 milliliters of solution? Same process. Molarity by definition is moles solute over liter solution. You got to get those two pieces. So step number A is we're going to take that 82.0 grams of calcium chloride and we're going to use that molar mass. To get it into moles. And you get 0.738 moles of calcium chloride. We're going to take the volume and take that 812 milliliters and get it into liters. And then we're going to take and combine them to get our molarity. And you get 0.909 molar calcium chloride. Questions? Since my thing's about to die, and since I know people are wanting exams, I am going to call it and head up to my office so people can come get exams. As you come into my office, state your name if there's a gaggle of you. Because I won't be able to, well, I guess I could just call them out real fast. Y'all are, and let y'all leave as you get them. That would make most sense, I suppose. Aiden. Kenzie Blanchard. Emma. I will be in my office except during XP today. Oh, just wait, please. Jair. Christina Charles. Bridget Primmon. China's not here today. Conlon Doss. Peyton Ingman. Alec Fields. Paris Flood. Conlon. David Ginger. Caitlin Hanson. Layla Harden. Lily Hood. Zoe Hubbs. Landon Humphrey. Kylie Jones. Cameron Joyner. Josh Kerr. Four, not Kerr, four. Kinley Keith, Wesley Lonius. Tan Mai. Wait, Wesley, they did on one. Martin, Kyle Payne, Kennedy Pilkington. Tyler Penny, Tyler Reed, Alexis Reedy. Sophia, Ty Ring, Alejandro Sanchez, Logan Sanders. Brooks Medley, Kinsley Sophos, Rin Tang, Amelia Young,